Hello everyone, I'm Billy Younger again, and this time I'm going to teach you how to compute a gradient. Let's turn it over to my document cam and check it out. So the gradient is actually a way of taking a scalar function and converting it into a vector, and it actually gives basically like a line of greatest descent or something like that. It really is the rate of descent or the rate of climbing on a particular curve. So for instance, we write it as the gradient of f, which might be a function of x, y, z. It could be a function of t and various other things. But the main thing is the gradient of this is defined to be basically this gradient, which is an operator, which means it's I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. And then in this case, it's actually acting on the function f of x, y, and z. So what that means is we get a vector whose ith component is the partial of f with respect to x, whose y component is the partial of f with respect to y, and whose z component is the partial of f with respect to z. And you see that you end up getting a vector basically whose x component is how rapidly f is changing with a changing x. In other words, if you go over a little bit in x, delta x, how much delta f do you go up by? Well, the delta f you go up by is the partial of f with respect to x times the dx, or specifically, it is the component of the gradient of f times dx. So delta f along the x direction is actually equal to del f dotted with dx I hat, or you can just write it times dx. But the main thing is that actually gives you an x vector. So that's really it. So if you had, for instance, f of x, y, z is equal to x squared plus y squared plus z squared, which is actually equal to r squared, then you really know f of x, y, z is really a sphere in three space. So the gradient of f equals the partial of this with respect to x. Well, that means basically that you're treating everything as if it were a constant except for the x. So this is like x squared plus 3 plus 4. So in this case, we get the partial of x squared with respect to x is just the same thing as the derivative of x squared with respect to x. So it's 2x I hat. The partial with respect to y is 2y j hat, and the partial with respect to z is 2z k hat. So that's actually the gradient. So notice it's really the partial derivatives aren't really any more complicated than the regular derivatives. You just got to remember to make sure you treat all variables other than the one that's in the bottom. You treat all of them as if they're constants. So x in this case, y in this case, and z in that case. If you actually were to plot this, I think you can see that it's basically going to have a slope of 2x, if you will, in the I direction, 2y in the j direction, or a component of gradient of f of equal to 2x in the I direction, 2y in the j direction, and 2z in the k direction. And that's sort of, I think you can actually graph it if you'd like to, and you'd see that it makes some sense with regards to being like a tangent line. And then the slope of that, of course, is what the gradient is. So hopefully that helps you compute a gradient. We're next going to use this operator, this del operator, which is defined to be I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. We're going to show you how to use that operator in a dot product, show you how to use it in a curl. When it's a dot product, it's called a divergence. When it's a curl, it's called when it's a cross product, it's called a curl. And those are actually critical things in vector calculus. So we'll show you how to use that. And I think that's pretty good for right now. Hope this helps. Have a good day.